In this set of lectures, that is lecture set 20, we will take a look at processes, what they mean, and how we can create processes, how we can create processes to run specific programs, all from a C program, or a bunch of C programs. Okay, so exactly what is a process? So a process is an operating system's view of a running program. So a program by itself, when it's not running, it's just a file that's sitting on the hard drive. And then when you run it, it's loaded into memory. It starts using memory to do various tasks. It might interact with the keyboard and mouse and the hard drive and the network and so on. The operating system has to keep track of all this, and so it sort of says what each process can do and makes sure that a process that you run doesn't sort of step all over other running processes, things like that. So that's a lot of security concerns that are important. That operating system makes sure that your processes don't mess around with other people's processes and so on. Okay, so Unix and Windows and Mac OS X are all multitasking operating systems. That is, they allow many programs to run, quote unquote, at the same time. So each running program is a process. That's how these operating systems, pretty much all the operating systems that are currently in use, represent a running program is through something called a process. So they're slightly different, but it's basically the same idea in almost all of these operating systems. So for example, two users can run the same program like VI at the same time. They don't interfere with each other's data because the operating system protects each of these processes from all others. Now it turns out later on, we won't get it in this semester, but later in more advanced classes we will see that processes can actually start to share data, but you have to be sort of careful about how you do that. Because of course you can if you're not careful, you can damage each other's data. So for now, you can think of each process as having its own little sandbox to play in, and that's completely different from all of the other programs that are running at any given time. Okay, so multitasking operating systems like Linux, Windows, Mac OS X allow each process to use the CPU in small bursts. So they're not actually running at the same time on a single CPU. If you just have a single CPU, and actually that's kind of hard to find these days, a single core machine is hard to find. If you had a single CPU, you would actually be able to see that the CPU switches between processes. Each process gets maybe a 20 to 200 millisecond time slices. Now, for more time-critical applications, you might see smaller time slices. So this small bursts of time that each process can run for is called a time slice. You get a time slice of a CPU, and it gives processes the impression, or it gives the user the impression that there are many programs running at the same time on a single CPU, but actually there's only one thing running at a given time. It's just that many programs get a time slice. So let's take a look at how we can sort of see this in Linux. So if I were to run the top command, you would see there's a couple of things you would see. Right now this is very lightly loaded. That is, there's very few programs really needing to run. There's always something running. For example, this graphical user interface is Xorg, or the X11 system. There's also parts of it is also in Ubuntu. This version of Ubuntu is using the Unity and GNOME interfaces. So all of those things are constantly running. They're taking a tiny bit of the CPU. So each of these programs are running for very short amounts of time, and for about 90% of the time or more, the CPU is not really doing anything. It's just looking for things to run. It takes very little CPU power to run these graphical user interfaces when they're not doing anything. Once you start doing something, sure, you'll see more CPU usage. So you can see that there's only, let me just take a look at this. These are the priorities. This is the top program is the one that's definitely running. And we actually never see anything change mode because this is so lightly loaded. But if you had a program that was sitting in an infinite loop doing nothing, it would be on top and it would show up as in the status. I believe it should show up as running. So you should see an R. Right now these are all saying that they are all sleeping. Okay, every once in a while we'll see an R like that. So most of the time all of these things are just waiting for things to happen. All these programs are waiting for things to happen, not really doing a whole lot. So it just happens to be the case when you don't have much happening on the system. Okay, so let's go back to our notes. So if you have a single CPU, once again, or a single core machine, it might look like there are many programs running at the same time, but it's really important to realize that it's actually just one program running at a given time. It's just that they switch back and forth very quickly. 20 to 200 millisecond time slices. So it looks like a computer runs many programs at the same time, but the CPU really only executes one at a time for very short periods, switches very quickly between all of the processes that can run, that are able to run. Okay, now we saw this before. This is the process address space. I'm hoping that you remember all of this. There's a few more details here. So this is how memory looks like to any given process. And so the Linux operating system, this is only for Linux. Windows has something similar, so as Mac OS 10, similar, but the actual numbers will be different. For example, the stack might be different in a different place, might be up here and might grow downwards on certain architectures, but on all Intel machines the stack grows towards lower addresses, so wherever it is located it will grow towards lower addresses. And that's because of the way the instructions of the Intel processors work. The stack always is decremented when you push something onto the stack. Other processes, like the ARM process, I'm not really sure exactly which way the stack goes on ARM processes, but it might go downwards. It might go to higher address. We don't know. I mean, I don't know. We could look it up. Okay, so a program is loaded into this memory area called text, and that's the space taken up by the contents of an executable file. So if you have a file, like for example your lab 10 program, it's just a file. It's just sitting on your file system until you run it. When you run it, it's loaded into memory, and it appears to be loaded to this chunk of memory. Although this is just, as we'll see much later, this is just a virtual address. All processes sort of think they're running at this location. Are they running at that location? No. It turns out that the virtual memory system maps this to a completely different physical DRAM location or address. Okay, so, but it looks, for all practical purposes, when you run the program and you use GDB, these addresses should make sense. Okay, so if you were to run a program VI, it'll get loaded once. If someone else, let's say some other user, also runs VI, it will share this executable. And so when two programs execute the same program VI, the executable and all of the shared libraries will be shared between these two programs. Okay. So now there's many things that you can use there's three main things that we will look at to query commands. One is top, which we already saw. I'll just take a quick look at it. There it is, it's still running, and if you wanted to figure out how to quit it, you've probably done this before. You just hit a Q and you're done. It constantly refreshes and shows you what all the top processor using programs are. This system is pretty lightly loaded. There's not much running on this system. Another way to check processes, you've seen this before, is to use the PS command, that is process status, and there's many options. So if you use just the simplest option, that is no options, you just see what's currently running in this terminal. If you say PS -A, you'll see a little bit more. It says that there's a bunch of other bash shells that are running, not being used. In this situation, this is because Ubuntu always starts up 6 shells in the background in non-graphical user interface mode, and then finally this one, that is this terminal window, is also running a bash shell. Okay, and then there's other options. PSAX gives you a lot more details and shows you actually pretty much all of the programs that are running right now. Okay, so I did PSAX. That is not -AX. There is a you want to be careful. PS-A will work. PS-AX. Actually, it works on this system. On some systems, you might run into a problem if you use minus with the X. There's other options. PS-AEX gives you even more information, gives you complete path names and all that. And then PS-AEXF shows you trees structure. So if this tells you that this GNOME PTY helper is running as a was started up by GNOME terminal. This bash that I'm running on in this window was started up under GNOME terminal. What is GNOME terminal? It's this window right here. And then under bash, I'm running PS. That is bash started up PS. Okay. Let's go back to our... And then finally, this is the one thing that you might not be familiar with, and we'll take a look at this very briefly for now. And this is the /proc file system. So cd to /proc. You should see it on all Linux systems. If you're using a Mac OS X, you won't have this. And there's a bunch of files in here. And if you can do an ls-l, but I don't want to right now because it'll give me a lot of data. Just want to quickly point out that these are all directories. This is in /proc. You cd to /proc. And if you do an ls, what you will see is a whole bunch of directories and a whole bunch of files. This turns out these are all not actual files or directories. These are actually all windows into kernel data structures. So each one of these directories is actually a process that's currently running. And so, for example, there is a process with the process ID 3133. You can cd into it and look inside, and you will see that there's a whole bunch of things. These are all kernel data structures relating to that one process. Okay, so we'll take a look at all of this in a little bit more detail in the very next video.